Why
Some
is
of
this
them
so
are
hard?
excellent, then others try to implement.
Oh, Gracia. Hi,
Oh,
Gracia.
hello, Kak.
What's wrong? You sound so sad.
Kak, I only got 70 for the last LM quiz.
Oh, that's not too bad. Why are you crying?
What do you mean it's not too bad? It's really bad. I want to be the very best in the class. And if I want to be the very best, I need to defeat Darren. And if I want to defeat Darren, I need to get 100, Kak.
Oh, I see. Okay. Well, what are you having a problem with?
So I don't really understand chapter 12, Kak, but I already understand some of the basic concepts.
Oh, good, good. Okay, how about this? I'll try teaching you, but let me prepare some materials in the library first, okay?
Okay, Kak, thank you.
Okay, it's ready now. You can come to the library.
Okay, Kak.
You see, there is, on the left part, there's a bunch of graphs. Do you understand this part?
Yes, I do. So in this chapter, the frequency is actually the variable and the impedance is the function of the frequency. And we are trying to observe the effect of varying frequency in these three elements that we have learned before, resistor, inductor, and capacitor. The first one is resistor, so impedance value of resistor is actually the resistor value itself.
Mm-hmm.
And when we try to sketch the graph, the magnitude and the phase remain constant at 0 degree. Therefore, we can say that the magnitude and phase of impedance of resistor is independent of frequency. The next one is for inductor. So for inductor, the equation is j omega L and also equal to omega L with a phase angle of 90 degree. So when we try to sketch the graph, at first it will be very low, the impedance, and in low frequency, the inductor acts as short circuit. However, when the frequency goes higher, the magnitude of impedance will actually goes higher too. Therefore, we can say that magnitude is actually directly proportional to the frequency.
Yes.
However, the phase remains constant at plus 90 degree. The next one is for capacitor. So for capacitor, the equation is 1 divided by j omega c and also equal to 1 divided by omega c with the phase angle of minus 90 degree. So when we try to sketch the graph, at first it will be very high because at low frequency, the capacitor will act as open circuit. However, as the frequency goes higher, it will become very low. Therefore, we can say that the magnitude of impedance of capacitor is inversely proportional to the frequency. And the phase of impedance of capacitor is constant, which is at minus 90 degree.
Mm-hmm.
And lastly, here, uh, when the three element is constructed in series, the equivalent equation becomes like this, and we can simplify it into the below equation. When we try to sketch the graph, the magnitude will be very high at first because, like before, the capacitor acts as a short circuit. However, at a certain point, it will become very low, which means that they reach the minimum peak value.
Mm-hmm.
However, as the frequency goes higher, the inductor will dominate the impedance. Therefore, the impedance will be very high as the frequency goes higher. The same also goes for the phase of impedance equivalent. At first, it will be minus 90 degree, which is the phase constant of capacitor. However, as the frequency goes higher, it will become plus 90 degree.
Mm-hmm. Oh, it seems you have a great understanding on all the components. What about this part? On the right of the board, there's transfer functions. Do you understand this part?
No, I don't understand this.
Oh, okay. So basically, in a circuit, there's always an input and an output. But for some different circuits, some frequencies will be allowed to pass through and some wouldn't. And that all depends from the linear network, which is where the transfer functions are, which is known as HW. So what transfer functions is basically the frequency-dependent ratio between the output and the input as seen in this formula. And on the bottom, you see there is a table, right?
Yes.
This table is basically the table of 4 transfer functions that can be used differently based on its usages. So the first one would be voltage gain. So voltage gain would be voltage output divided by voltage input. For current gain, it would be current output divided by current input. For transimpedance, it would be voltage output divided by current input. And do you know what it would be for transadmittance?
It will be current output to the voltage input, right, Kak?
Yes, you're right. Okay then, how about let's look for more resources on this topic?
Yes, Kak, let's go.
Where is the book?
Wow, what is going on here?
Oh, hello, Pak Dani.
Hello, sir.
Oh, what are you doing here, Gracia?
I'm studying for the exam, sir,
Oh,
about chapter 12.
chapter 12? I thought I already teach you last week.
Oh, but I still don't really understand about this chapter.
Oh, you still don't understand? Oh my. Okay
Yes.
then. I can teach you again.
Yes, sir, please do. But, sir, I'm very hungry, so can we do it at the kitchen, sir?
The kitchen?
Yes.
Wow, okay then.
I have already prepared for the food.
Oh, that sounds
Wow.
yummy. Let's go.
Okay.
Wow, look at this.
Oh,
Yes.
you already prepared lots of food here.
Yes, sir.
Okay. Let me get my materials ready. Okay, so before Kadevita teach you until which part?
About transfer function and the basic concept, sir.
Oh, I see. Okay then, so this is perfect. This one is actually an example of a stereo amplifier, and if, for example, I have a voltage output here and a voltage input here, the gain would be voltage output divided by voltage input, or the Vs. Now, we can actually expand this by using the Vn. So, Vo divided by Vin multiplied by Vn by Vs. So, do you know what S here represent?
Is the G omega.
Yes, S is equal to the J omega. And basically we use this because later on the circuit equation will be very complicated with so many J omega. So we can just use S to simplify things for us. Now, we want to find Vn. So we can use the voltage divider formula. So this one, with the voltage divider formula, we can just do Rn divided by the total impedance, Rn plus the impedance of capacitor, 1 by Scn. So this is the equation that you get multiplied by the Vs. Now, how about the output? We also do the same thing. We find the voltage divider formula across the capacitor O. So 1 by SCO divided by the total impedance, RO plus 1 by SCO, multiplied by the dependent source, 1000 Vn, this one right here. And so what we will get is V output is equal to this formula right here. And then we can just input everything into the gain function formula. So after inputting, we can cancel out many variables and we are left with this equation. Now, this equation is not really that nice because we have a fraction in the numerator and denominator, and so we can just multiply everything by a constant. So for this one, we multiply everything by SC0, and this one we multiply everything by SCN. So what we will get is this simplified form. Now, we can just input all the values of the variables, and this is what we will get. Okay, after that, we can actually simplify it even further. We want to make the S constant into 1. So what we can do is that we divide everything. In this case, it divide everything by 79.58, and for this one, we divide everything by 3.18. So this is what we get. Now, if you notice, 1.258 times 10 to the power of 5 is almost equivalent to 40,000 pi, and 314 is almost equivalent to 100 pi. So what we can do is we can substitute everything with the radian form, and this is now the gain function of the circuit. Do you understand now, Gracia?
Yes, I do, sir.
Okay, that's great.
And from this equation, we can actually determine the poles and zeros. But before we do that, let me explain to you what poles and zeros are first. basically what poles and zeros are basically the frequencies for which the value of the denominator and the numerator of the transfer function become zero respectively. The values of the poles and zeros of a system determine how well the system performs. So from the numerator we can determine the zeros, and from the denominator we can determine the poles. From this graph you can see that when the numerator is 0, then it will be at 0 on the bottom. And when the denominator is 0, it will be infinity. So let's try going to this example question that is based off of Pak Dedi's circuit. Okay, so this is the last equation we got from Pak Dedi, right? If we simplify it, it can become like this. So do you want to try finding the zeros and poles from this equation, Garcia?
Yes, we factorize it, right, Kak?
Yes.
So the zeros will be 0 and the poles will be minus 100 pi and minus 40,000 pi.
That's right. But the thing is that they are still in radian form, and the question is asking for the frequency. So we use this formula to find it. So if the zeros are 0, then that would mean that the hertz is also 0. And for the poles, the first one, if we use the formula, we will get negative 50 hertz, and for the second one, we will get negative 20,000 hertz. And the question also asks for the constant. Okay, so how to find the constant is basically finding the multiplication factors from the equation. So in our case, it would be 40,000 pi and 1,000. So if we multiply them together, we'll get it, which is 40 million pi. So that is how we get the frequency and the constant. Do you understand?
Oh, yes, Kak, I do.
Wow, that's great.
Wow, that's great, guys. Yeah. So, are you ready for quiz next week?
No, sir, I'm not.
Hey,
Bye-bye.
Thank you for
Thank you
listening.
for listening,
Thank you for
everyone.
listening.